In a 2001 paper, Nick Bostrom argues that given some plausible premises, it's almost certain that we're living in a computer simulation. The premises are that there's a non-trivial chance that humans will reach a stage at which they can and do run many simulations of the world, where the inhabitants of the simulations are conscious. From this he calculates that the vast majority of conscious beings existing will be simulated. If so, he claims, we should believe we're living in a simulation. Now you might be wondering whether simulations could become conscious, but that won't be my focus today. Here I'm interested in the last step of the argument. Specifically, even if we grant that the vast majority of conscious beings are simulations, does it follow that it's probable that we are in a simulation? Hello, and welcome to Causal Foundations. I'm Naftali Weinberger, a philosopher of science who's been researching causal models for over a decade. In this series, I introduce foundational concepts from causal inference in videos of approximately 10 minutes. You don't need to have seen earlier episodes in order to understand today's, but I do need to tell you how it connects. Last episode we discussed a principle called faithfulness, which more or less says that causation implies correlation. This principle is violated when a cause influences its effect via two canceling paths, where the parameter for each arrow gives the strength of its causal relationship. We then saw an argument that uses the fact that the set of canceling parameters is very small compared to the whole set to conclude that cancellation is improbable. So what does all this have to do with simulations? Both this argument and Bostrom's move from a measure theoretic claim that involves counting possibilities to a claim about how probable they are. In Bostrom's case, it's an inference from the comparatively large number of simulated beings to a conclusion about how probable it is that we're one of those beings. But are such inferences valid? I'll accept for the sake of argument that the number of conscious beings not in simulations is small compared to the set of simulated conscious beings. But this by itself doesn't tell us how probable it is that anyone is in a simulation. To see why, suppose someone claimed that there's a 3% chance that an American not from Alaska comes from Wyoming, since Wyoming takes up 3% of the continental U.S. You'd immediately respond that a state's size is not a good proxy for how probable it is that someone lives there. This reveals that you don't get from premises about size to conclusions about probability without assumptions about how these relate. Let's get a bit clearer about what we mean by probability. The concept of probability actually leads a double life. Probability sometimes seems to refer to something objective. If a coin has a 50% chance of landing heads, it will land heads roughly half the time. The exact relationship is complicated, since a 50% chance does not rule out getting 10 heads in a row. But presumably there's some objective relationship between the probability and the physical properties of the coin. On the other hand, probability might refer to how confident we are. If I say I'm 90% sure that a political candidate will win an election, I'm expressing a high level of confidence that this will happen. While I hope this belief is based on good evidence, it is first and foremost a subjective claim about my mental state, and I'd expect it to change as I learn more. Finally, we can try to formulate objective norms about how reasoners should interpret their evidence. Any such norm will be controversial, but most people do believe that there are better and worse ways to interpret evidence. There's one such norm that's very tempting. It says that if you're in a state of total ignorance as to which of a set of possibilities obtains, you should assign an equal probability to each possibility. So if you're given a 6-sided die and know nothing about it, you should start by assuming that the probability of each side is 1 in 6. This is called the principle of indifference. The problem with the principle of indifference is that what it tells us depends on how we count the possibilities. If we count Wyoming based on its area, we get 3%. but if we count it as being one of 50 states, we get 2%. This phenomenon generalizes. Consider a factory that produces squares with sides between 0 and 2 feet. The principle of indifference suggests that half the squares would have sides that are less than 1 foot. But we could describe the very same factory as producing squares with areas between 0 and 4 square feet, leading us to believe that half the squares will have areas less than 2 square feet. Since these proposals are incompatible, the principle of indifference yields inconsistent results. Since the principle of indifference is a non-starter, how should we think of arguments like the ones I began with? I'll start with the causal case before turning to the simulation argument shortly. The causal argument concerns the probability that parameters cancel. But there's something strange about assigning probabilities to parameters. In previous episodes I explained that the variables in causal models are random variables with an associated probability distribution. Given a causal model and probability distribution, the causal parameters are fixed, at least when the effect is identified. And this is confusing, since in debates over cancellation, people often talk about the parameters varying. But parameters don't vary. They're fixed. Let's return to Daniel Steele's example from the last episode, in which a city tries to reduce speeding by hiring more police. In this model, the probability of speeding given road improvements is fixed. Omitted causes of speeding get lumped into the error term. But the effect does depend on the number of police, which we can include in an augmented model. This model can represent how the effect of road improvements on speeding depends on the number of police. Now here's the subtle part. When people talk about changing the parameter for the effect of road improvements on speeding in the model on the left, what they're really thinking of is changing the number of police in the model on the right. And this means that we can talk about the probability of the parameter by referencing the probability distribution for the police variable. We can now represent the factors influencing parameters as additional variables in an augmented model. The reason for cancellation is that the city hires only enough police to counteract the increase in fatalities. This means that the number of police they hire depends on beta and gamma. We see that the original model omits a common cause, going against a standard assumption of causal modeling. So suppose we assumed there were no omitted common causes. Would it follow that cancellation is improbable? Not quite. We still have no basis for assigning specific probabilities to the parameters. But any cancellation would have to be coincidental, in the sense that there could be no correlation between parameters. And this might be enough to assume it's not happening until proven otherwise. The reasoning here is not all that different from when we're skeptical of conspiracy theories that require everything to align just so. We can be justifiably skeptical of such fine-tuning without assigning it a specific probability. Let's return to the simulation argument, which assigns probabilities over conscious beings. What's subtle here is we're considering hypotheses about whether we, as conscious beings, are or are not living in the simulation. When I wonder whether I am living in a simulation, the belief I'm entertaining is called a self-locating belief. To illustrate this concept, imagine I wake up one day and am told that while I was sleeping, an evil scientist made an exact clone of me, and I don't know whether I'm the original or the clone. The question of which one I am is a self-locating belief. It concerns which one I am. The philosopher Emily Adlam distinguishes between pure and superficial self-locating beliefs. A superficial self-locating belief is one that can be established based on non-self-locating evidence. If I know that the clone is in a different location as the original, then I can figure out who I am by figuring out where I am. In contrast, a pure self-locating belief cannot be resolved in this way and can only be expressed first personally. I can know all the third personal descriptions of every individual and still not know which one I am. The conclusion of the simulation argument is a pure self-locating belief. We can have full descriptions of a simulated and non-simulated being and still ask, which one am I? Emily Adlam compellingly argues that there's no objective basis for assigning probabilities to pure self-locating beliefs. After all, there's nothing we could third-personally specify that would support one probability assignment over another. So it would be like trying to assign probabilities to die rolls, while stipulating that we know nothing about the physical properties of the die. To assume equal probability is just to apply the principle of indifference. Since the simulation argument involves a pure self-locating belief, it follows that the last step of Bostrom's argument does not go through. This doesn't mean that we're not living in a simulation. Perhaps there's a way to fill in his argument without appeal to probability, as we did in the causal case. The moral of today's episode is that we need to be careful when using probability theory to model features of the world, since there may be domains to which it no longer applies. Thank you for listening. For further information, check out the sources in the show notes. And if you've gotten this far, don't forget to like and subscribe.